How are we doing, guys? So this video is on simple harmonic motion. It's based around exercise 13b from Fundamental Applied Mathematics, page 224 there. And I'm going to be looking at questions 2, 5 and 6. I'll just say first of all, if you haven't watched my video sine waves and cosine waves, I'd suggest you go and watch that first, just for some of the maths behind this stuff. So first of all, what is simple harmonic motion? Well, here's our definition. It is movement about a fixed point here such that the acceleration is always proportional to the displacement and in the opposite direction. So it's movement like this where you're moving out, hitting some maximum point here and then moving back in, hitting the same maximum point in the far side. And so it's just a movement back and forth like that. That's simple harmonic motion. And it describes a lot of things in physics. The most common one you'll see in the Leaving cert is problems based around things bouncing up and down on a spring or bouncing across on a spring. Problems about tides. Tides follow simple harmonic motion as well. And just to develop some of that, displacement is how far you are from here. Okay, so there's a positive displacement and it's going to have some corresponding acceleration in the opposite direction. So if you imagine this was on a spring, when you are a little bit further away from maybe an equilibrium point, you're going to have a bigger force in, okay, causing a bigger acceleration. For a larger displacement, you will have a larger acceleration, okay? That the larger the displacement, the larger the acceleration. They're always in the opposite direction. If displacement becomes negative, okay, you'll get a positive acceleration. And so the equation that describes this is acceleration is proportional to displacement. A is proportional to x, where for the moment we'll just say that's a constant. We'll meet it again in a few minutes. So acceleration is proportional to and in the opposite direction minus. Now very often when we do this in practice, because if A is positive, x is negative, and if x is positive, a is negative. This minus sign, we can talk about the magnitude of the acceleration is omega squared times the magnitude of the distance. So we'll ignore that minus sign from time to time, or well, regular enough. So just some of these other equations, these are all on page 54, and I'm going to put up another video showing where some of these equations come from. V squared is omega squared times a squared minus x squared. We're just going to accept on faith for the moment. This is very similar to the acceleration equation you saw in circular motion. In fact, it's the same equation. We'll talk about why in just a second. The period is the same as in circular motion. It's 2 pi divided by the angular velocity. It was what it was in circular motion as measured in radians. Now it's called the angular frequency, okay? But again, they're very, very similar concepts. We met this equation in this video on sine waves up here. We met a sine omega t. There's a plus epsilon there as well. More often than not, you're going to see that as just a sine omega t, okay? The epsilon is called an offset. That's if you're not starting at either the center of the motion or at the maximum point of the motion. But we saw in that video that this is a solution to this equation here, okay, where acceleration a is the second derivative of x. That this is one possible solution. Another possible solution we saw was a cos omega t, and we'll see that when we start at one of the extreme points out here, okay? So the choice of equation here depends on your starting point. So yeah, just A stands for amplitude. Okay, so your amplitude is how far from your starting point, from your center point, your maximum distance is. Okay, so you got the same amplitude either side in a simple harmonic motion problem normally, that your particle or whatever it is moving around a fixed point. It'll be the same distance either side. The displacement we've talked about, acceleration we've talked about. Okay, so let's get this idea of angular frequency hammered down a little bit. Simple harmonic motion can be thought of as circular motion projected onto the plane, onto a 2D surface, or 1D surface even, sorry. So if I look at these two lines here, I'm going to attempt now to show you how circular motion with my pen, thankfully I've got the lamp here. If you watch the shadow of my pen, as I move in a circle with my pen, the shadow is going to move between those two lines. And the shadow is moving back and forth with simple harmonic motion. Okay, so my pen might have some angular frequency or angular velocity, omega, and that corresponds to how fast the pen, if I move my pen faster, you see the shadow moving faster. So a faster angular frequency corresponds to faster movement, essentially, and to a smaller period, the period being the time it takes to go from here to here and back again. Okay, so as I keep doing that, I just want to point out, the angular frequency is related to circular motion, and it tells you how fast you're moving. That if you watch the shadow, okay, it kind of lingers around here, and it lingers around here. That's the point at which you're moving slowest. You're moving fastest here in the middle. Okay, so the shadow is moving fastest when it's transitioning through that middle point, and it's moving slowest. In fact, there's a point down here where it stops moving because it's moving towards the line, stops moving, and then it's moving away from the line. So it's moving at a point out here, it has zero velocity. Okay, so maximum velocity always occurs in the center of simple harmonic motion. Let me show that again here. If this is our full amplitude, okay, there's our central point. There's another full amplitude. Okay, so maximum velocity. Okay, and out here, velocity equals 0. Similarly, out here you have your maximum acceleration. Okay, just as you're about to turn around, and therefore your maximum force as well. In here, okay, when the thing is moving in, it's accelerating less and less and less. As it crosses this point, the acceleration will be 0. And we'll be using that fact later on with some of our questions. So I said we'd have a look at questions 2, 5 and 6. I'm going to have a look at 9 and 10 in a separate video. So question 2 asks us, a particle moves or performs simple harmonic motion about a fixed point O. When its distance from O is √7 meters, its speed is 9 meters per second. When it is 2 meters distant from O, its speed is 6√3. Find the amplitude and the periodic time. Okay, so we're told in the question that when x equals √7, v equals 9 meters per second, and when x equals 2, v equals 6√3. Okay, which is 36 times 3 is 108. √108 meters per second. So just for context, what you're looking at here is something moving with simple harmonic motion. You're being asked to find the amplitude, so you don't know what that is, but you know that when you're when you're √7, which is 2 point something, so when you're 2 point something meters out, √7, you've got a speed of, at this point, the velocity is 9 meters per second. When you're 2 meters out, a little bit less, sorry, that's √7, 2 meters out, your velocity is now √108. Okay, so it's gone higher. Velocity there at this point is √108. Okay, so that's 10 point something meters per second. So to solve this, we're going to use our v squared is omega squared a squared minus x squared formula. Okay, that we'll be looking at in another video, but let's take it on faith for the moment. V squared is going to be 108 squared. Omega squared, we don't know. A squared, we don't know. But the corresponding value for x there is 2 meters per second, so that's 2 squared. Okay, and from here we can say v squared is 81. So this is at 2 separate instances. We're going to look at what happens in this equation. Here's 1, here's 2. 81 is omega squared times a squared, which we still don't know, minus root 7 squared is 7. Okay, so we can divide these equations by each other. We can say 108 over 81 is the same as omega squared a squared minus 4 over omega squared a squared minus 7. Okay, and then omega squareds cancel, so now we have an equation that only has one variable, a squared. Cross multiplying, we get 108 times a squared minus 7 equals 81 times a squared minus 4. And we can say 108 a squared minus 108 times 7 is 756 equals 81a squared minus 81 times 4 is 324. So moving things around, 108a squared minus 81a squared equals 756 minus 324. So we say 108 minus 81 is, that's 27a squared equals 756 minus 324, and that's 432. Dividing through by 27, 432 divided by 27 is 16. A squared is 16. A is always a positive number in these, so that's going to be 4 meters. So that's a 4 meter amplitude that we have. And then we come back and find omega. So it doesn't matter which one. I'm going to work with 81 equals omega squared times 4 squared minus 7. Okay, well that's 81 is omega squared times 16, take away 7 is 9. Divide through by 9, you get omega squared is equal to 9. So omega is equal to 3. Okay, so 3 is your angular frequency. And if you wanted to here, do they ask for find the amplitude? We have, they want the periodic time as well, t. And the periodic time is always 2 pi is 1 full period. That's the time it's going to take to go from here to here. Oh, sorry, that's the angle it goes through. If you imagine my circle, again, the shadow of my pen has to go through a full 360-degree rotation. I need to turn this sideways to get this to work with the lamp, sorry. But to go through a full 360 degrees or 2 pi, to move from here around 1 period. Okay, that is across, back, and back to where it started. So it's 2 pi divided by whatever its angular frequency is in radians, and that's 3 radians per second, and that gives us 2 pi over 3 seconds is our periodic time. You can go to your calculator if you want that. 2 pi over 3 is 2.09 seconds. Okay, so how long this thing is going to take to go from here out and back to here again. There's question 2. Question 5 says a particle performs simple harmonic motion about a fixed point p. When its distance from p is 1 meter, its speed is 3 meters per second, and its acceleration is of magnitude 3 meters squared. Find the maximum acceleration. So we've got x equals 1 meter when v equals 3 meters per second and a equals 3 meters per second squared. Okay, so straight away with a equals omega squared x. Remember, I'm kind of ignoring the minus. I can say that 3 equals omega squared times 1, and that omega is the square root of 3. Okay, so that's my angular frequency, is root 3 radians per second. So I want the acceleration at the maximum acceleration, I suppose. So if this is our point P that we're moving about, the maximum acceleration, remember, occurs out here. Okay, a max when the acceleration, when the amplitude, when the distance from P is at the full amplitude equals a. So when x there is 1 meter, we know we've got an acceleration at that point of 3 meters per second squared, and we've got a velocity of 3 meters per second. We're interested in the acceleration out here. Okay, so the velocity is going to be 0 at that point. Acceleration is going to be what? Well, to get it, the acceleration is going to be omega squared, we know, times the distance, which is the full amplitude. We need that full amplitude. So come back to v squared equals omega squared times a squared minus x squared. And we are going to get ourselves 3 squared equals root 3 squared times a squared is what we want, minus x squared is 1 squared. Okay, so that says 9 equals 3 times a squared minus 1, which means dividing through by 3, we get 3 equals a squared minus 1. A squared, bring the 1 over, equals 4, and a is 2. So the maximum acceleration, according to a, is omega squared x. Well, that's going to be root 3 squared times x, is when the amplitude is 2. Root 3 squared is 3 times 2, that's 6 meters per second squared is the maximum acceleration this thing is going to experience. That's when its speed is changing the most, is out at that point there. Last question I said I'd have a look at was question 6. So a particle performs simple harmonic motion about a fixed point O. When it is 5 meters from O, its velocity is of magnitude 24 meters per second. Its acceleration is of magnitude 20. Find the amplitude, the periodic time, and how many complete oscillations it completes in 1 minute. Okay, so this is quite similar to what we've seen so far. So I'll do it kind of quick. When it is 5 meters from O, so when x equals 5, velocity equals 24, and acceleration equals 20. So we're going to do the same thing we did. A equals omega squared x. Tells me 20 is omega squared times 5. Omega squared then is 4, and omega is 2 radians per second. They've asked us in part 1 to find the amplitude, so that's going to be using v squared is omega squared times a squared minus x squared, which is 24 squared equals 2 squared times a squared minus 5 squared. So that's going to be 24 squared is 576 is 4 times a squared minus 25. 576 divided by 4 is 144 is a squared minus 25. Move that over, you get 169 is a squared. The amplitude is 13 meters. The next thing they asked was the periodic time. Well, t is 2 pi divided by the angular frequency. So that's going to be 2 pi over 2 radians per second. And that's going 2 pi radians over 2 pi radians per second. And that's going to be pi seconds, or 3.14 seconds roughly is our periodic time. And the last part says how many periods or how many complete oscillations does it perform in 1 minute. Well, 1 minute, that's 60 seconds, okay, and it's doing an oscillation every 3.14 seconds. So that gives us 60 divided by 3.14 is 19.1, but that's 19 complete oscillations. Now, I'm going to make another video on questions 9 and 10. I'd encourage you to try maybe 1, 3, 4, and 7. If you want to wait for 8, it's similar enough to question 10. If you want to give it a go, you're welcome to as well. Okay, see you next time.